somewhere. Okay. Okay, and this is working. And how to change the page? Okay. And this one. So, still good morning to everybody. Before I start my talk, I would like to thank the organizers for invitation to this workshop and to the whole program. And I think we have quite reduced participation in this workshop because of various reasons. And I will speak today about the title of my talk is kind of a different version on the given here, slightly different. It's stochastic nonlinear Schrödinger equation driven by Lévy noise in the Marcus canonical form. Right? And this talk is based on collaboration with my former PhD student Jiahui Zhu and Liu, who turns out to be former PhD student of Michael Reckner, who is in the audience. So I will start with deterministic equation. So we consider a nonlinear Schrödinger equation. So U is a complex number depending on time and space variable. It is I Laplacian U. So if lambda is 0, that is classical Schrödinger equation without potential. If sigma is 0, then we have a classical Schrödinger equation linear with a constant potential I lambda. The nonlinear equation appear in many applications. In particular, one of those applications is photonics. And so what I understand is that the people in photonics consider some sort of a long cable, and the length of the cable is for them Z, but interpretation is T. So in those photonics, there's the space variable here, which is bounded, and the role of time in our equation is played by the length of the cable. And such cables apparently are put on the bed of Atlantic Ocean, and properties of such equations are in particular very important. So when we look at this equation, the constants are written in such a way that, so the constant lambda is real constant, that as in the linear case, the L2 norm of the solution is conserved or preserved, provided the solution is regular enough. But because of the nonlinear structure, there is also energy conservation. And the energy conservation consists of 1/2 Dirichlet norm, so 1/2 gradient U in L2 space squared, plus some part coming from the nonlinearity, which, so there is a constant lambda divided by this power 2 sigma plus 2, and multiplied by the Lebesgue norm of the solution in appropriate power. And formally speaking, one can prove this conservation, but just simply differentiating the equation, this formula respect to T, using integration by parts. So when you look at the energy, there is important difference between lambda positive and lambda negative. The lambda positive is called the defocusing case, which is easier, and the focusing case is lambda negative. The reason it is easier is because the energy is conserved, and when lambda is positive, all terms are positive, which from mathematical point of view make it easier to do various estimates. And okay, so next page. So this, apart from the conservation, there is also some invariance of the equation with respect to various scalings. And for instance, what it means that if I take U, which is a solution to my equation, and I define a new solution, a new function, on the right-hand side, then the new function will be also solution to the equation if I choose theta to be 1/2. If I choose different theta, then the energy, the mass will be preserved. If I choose different theta, then the energy will be preserved. And this leads, but I will not speak about this, to various form of critical exponents, which sigma equal 2/n is the mass critical, energy criticality is number 2/2 minus n. So n is the space dimension. So the whole talk is when this variable x belongs to the Euclidean space R to power n. So this picture is not really applicable to my talk because here this domain would be bounded. So I will move to the main part of my talk, which is nonlinear Schrödinger equation, stochastic notation. So for various reasons, this is also the case of this photonics example. One would like to consider the equation with some noise. And now there could be various noises. Very often the good noise is the additive noise, which does not depend on u, but often the noise has to depend on the solution u itself, and such noise I will consider in this talk. So let us start with the case where we have a Gaussian noise. And we consider a special form of the Gaussian noise. So we consider Brownian motion of Wiener process here. The way it is written, it is as if it was one-dimensional, but actually one can do multi-dimensional, even infinite-dimensional noise with sufficiently good properties. And the coefficient g, which is written here, is a special form. So g depends on the value of our solution. So g depends on the complex number z, and it is in the form g tilde of z squared, and g tilde is real valued function multiplied by z. So when g tilde is constant, we have a linear equation. So no, when g is constant, we have a function g being linear, and then the equation is called bilinear equation. But we are considering more general g tilde, and then this term, this Stratonovich differential, is interpreted in the way that it is Ito differential plus Ito correction, or Ito Stratonovich correction, which is again here is a linear respect to u, but the coefficient depends in a nonlinear way. And so the advantage of this is that the Stratonovich differential implies, for instance, you can need to prove it like a meta theorem, that the L2 norm of the mass is preserved, but also has some other properties which I mentioned in a moment. So the advantage of such equation is that the mass is preserved, and that is the main feature from the point of view of my talk. And such equations were first studied by Ander Board and Arnaud de Bourge in Communication Mathematics and Physics 1999. They considered the bilinear noise. So the coefficient was linear respect to u. And the main tool for the estimate in order to handle the nonlinearity was such a Strichartz estimate. So they proved that if you take any nice process u, which is kind of progressively measurable, and you consider this stochastic convolution process, and you take this stochastic convolution process in appropriate parameters p and r, which I didn't write it down here, it's my fault, then you can estimate this norm in Banach space using the norm of the process u in the space LQ respect to time L2. And such estimate is important, plus deterministic Strichartz estimate, which I do not mention because it is the generalization of the deterministic Strichartz estimates, because it implies the existence and uniqueness of global solution by some fixed point argument. And so what they assume that the nonlinearity is rather small. So this is a subcritical case. And they extended the results in various ways, in particular in those two papers, 2002, 2005. Another extension which I mentioned here is my paper with Animier from 2013, and where we considered Schrödinger equations which were fit to consider this photonics case, because our domain was bounded domain of virtually bounded compact manifold. And one of the tools was a new type of Strichartz estimate, where the parameters P and R are the same as in the case of the Beauvoir-de-Bouche, which is admissible pair. But the estimates we were able to prove were stronger, and that we got somehow stronger results, because here we get only L2 exponent 2 respect to time variable, and that is kind of important. And I mentioned this result because this tool is sort of important from the main result I'm talking about today. One should mention many other papers on the topic of stochastic Schrödinger equations, in particular by Michael and his collaborators, so Barbu and Zhang. And there are a few mentioned, probably there are many more. There was a principal difference in approach between this group of people and others. They use something called Dot-Sussman transformation, and they were restricted, if I understand, to bilinear case. There is a paper by Fabian Hornung, two of the papers. Oh, I will ask. I'll have to find out. Yeah, I've seen my name being written wrongly, but I didn't see your name being written. Okay, so at least my name is written correctly, yes, which often is wrong. So anyhow, there are papers by Hornung, who in the first paper he did a different proof of some results from Michael and Zhang, and we have also a few papers with Fabian and Lutz Weiss on the existence of solution to such nonlinear using compactness method, because I mentioned before they were mostly based on fixed point arguments, and we have also another result about uniqueness in critical case. But what I'm talking about here is the equation with Lévy knots. So the nonlinear part is the same. What is different is the noise, and the noise is written with this diamond symbol. So the L now is the Lévy process, and actually what we're interested in Lévy process with pure jumps. And for simplicity, we consider the Lévy process finite dimensional Lévy process. So the LJs are components, and there's still just a notation. So the question is, how do we define such solution and why? So when I spoke about Stratonovich equations, I said that the main consequence of Stratonovich equation was that the mass was conserved. So we actually have chosen this noise in order to prove that the solution exists and the mass is conserved. And this presentation is called Marcus canonical form, and I learned about it from David Applebaum, who actually described it well in his book. So in briefly, what you do, you consider those vector fields Gj, which are vector fields on C. Then you consider this auxiliary equation, where Gj is multiplied by some coefficient Zj. Z is a vector in Rm, so Z is like describes the size of the jump, and you consider the global solution of this problem starting from any y. Then you put time 1, and you have notation phi, and this integral, which is written over there, is equal. Forget about the continuous part of the Lévy process is equal the integral respect to this continuous, so eta1 plus some correction term, which is different than in any other. So there is a special way which was actually introduced by Marcus, forgot his name, in the 70s, and it was developed by Kunita and Applebaum. So to be more precise, we consider Lévy process without large jumps. Actually, I don't know how to deal with big jumps, which maybe is easier, but I don't know. Maybe it's easy. And in this case, the equation which I've written can be written using this form. Here, the n tilde is a compensated, disappeared, Poisson random measure corresponding to process L. And this is a term which uses this flow phi, which I introduced before. And here is the jump measure nu. So that is the equation we want to study. So you can say, one can completely forget about this notation. We say, OK, we study this equation where phi was defined before. And what we expect is, so this equation Marcus form, what we expect is that the classical rule of differentiation, Wong-Zakai approximation, and the conservation of L2 norm. And such things are well known in finite dimensions, so there is just extension of this to Schrödinger equation. So what are our assumptions? So we consider this Marcus form. We assume, as before, that those GJs are smooth functions of the form GJ tilde real function multiplied by y. And those functions GJ are Lipschitz, but also these guys are Lipschitz. So they're quite strong assumptions on the function G. And what we look at this equation, which I have written before, where now it's written that n tilde is a compensated Poisson random measure corresponding to the Lévy process L. And the intensity of this Lévy process is nu tensor product Lebesgue measure. So nu is the corresponding Lévy measure. OK, so now this is a problem we want to study. What about how to do it? So here are some properties of the flow map phi. So okay, it starts from y. It has some Lipschitz properties which are listed here. Remember that this phi depends on 3 parameters. Actually, theta, we take theta 1, so it will be just 2 parameters. We have additional notation and check those properties which are needed. And what about the result? So first we look for local Mach solutions. And the local Mach solution is a process which is defined a priori up to some stopping time. And we assume that this stopping time tau is approximated by some sequence of stopping times tau n, which is increasing. And the process up to time tau n is Cadillac with values in L2. This process up to time tau n is bound with respect to L2 norm, and it has also integrability condition where the P and R are the same numbers which were in the Strichartz estimate. And moreover, it satisfies the mild form of our stochastic Schrödinger equation. So the mild form means that we use the group generated by the operator S. We replace the equation by integral form. The only thing is that we have to take care about this part which is in blue here, because the blue here means that we first define a certain process I, and then we take this process, taking the values at time t minimum tau n. So this process I is defined by this formula using Poisson random measure. The warning is that some kind of if I would like to do it differently in a straightforward way, then this would be incorrect because the process here is not predictable, so it cannot really make sense. So once we have the local solution, we also have definition of the maximum local solution. And what is the maximum local solution? Is such a local solution which cannot be extended. So it is maximum element in the class of all local solutions. That's definition from David Ellsworth's book. And So what are the results? So first of all, we have results that generalize the inequality from my paper with Animier, that if I consider integral respect to Poisson random measure, then a certain Burkholder-Davies inequality is satisfied. So the expected value of supremum in some appropriate Banach space to power p is bounded by some quantities related to the integrating process. Then what is next is that that inequality could be used to prove the generalized Strichartz estimate, or this is still not Strichartz, the maximum inequality, but maybe I jump this, but then you have a Strichartz estimate. So I mentioned already deterministic Strichartz estimate. So this Strichartz estimate involves this admissible pair P and R. And what it says is that if I take initial data phi, then the trajectory is integrable respect to power P respect to time with values in R, but only integrable, and it satisfies this condition. And this can be generalized to the inhomogeneous Strichartz estimate as it is here. And this inhomogeneous Strichartz estimate can be generalized to what we proved with these two people, namely, if I consider stochastic convolution process with respect to Poisson random measure. The expected value in this space is bounded by two elements with respect to integrating process psi. And there is a very tricky proof of that inequality. And this
5 more minutes, please.
5 minutes, yes. And this proof involves using the Burkholder inequality, but in the space of trajectory. So we consider this expected value, usually you would say in LR, but we look at it in LP of R. And using that this space is also good for the point of view of Burkholder inequality, we derive what we need. So the tools were Strichartz estimate. Now, what about the result? So result is from last year from Journal of Functional Analysis, that if we consider the same condition sigma as in the first papers by de Bush, so it's subcritical, then, so the sigma is quite small, there exists a unique global Mach solution to our problem, such that the L2 norm is bounded. For every t, the trajectory belongs to the LP-LR space and is integrable. And most importantly, what I say is that the L2 norm is preserved, mass is preserved. So that is the result. How do we prove it? So the first step is change the equation by some sort of truncated equation. Means we introduce appropriate truncation, and we prove that this equation is well posed. And like in the previous talk, we prove that this equation is well posed first on this time interval for small t. Then, unfortunately, much more complicated is to prove that this small t can be, or small t0 extended to the whole interval. So by this way, we get a solution to our equation on the whole time 0t, and t is arbitrary, so we get what we get a global equation, global solution to our truncated equation. So how we get the solution to our original problem? So to get the equation to our original problem, we introduce a stopping time tau k. And the stopping time tau k is something that if before this stopping time, the truncation is just 1. So once we introduce the stopping time tau k, we get an equation, which I don't know what happened. Here's, I made some changes, and there is a mistake. Here should be used. So before the stopping time, we get actually solution to our problem. And when we put together those solutions to our problems before different stopping times, we get a solution to our equation. The only problem is that this solution exists on the time 0 tau infinity, and this tau infinity may be finite. So the important clue point is to prove that this tau infinity is infinity. In the first step, one has to show that this solution we constructed preserves the energy. And finally, the main difficult part is to prove that our solution satisfies certain energy estimate, namely that for every t, if I consider my UK is the approximate solution in this LR space, that this supreme over k is finite. Because if we prove that this rho is finite, by using Chebyshev inequality, we can prove that tau k probability large equal to t converges to 1. And the most difficult part is this one. And to prove this step, we use some idea from earlier paper by Fabian Hornung, and that we at the end prove that the solution is global. So thank you very much.
Are there any questions?
Well, thank you very much. This was so my very natural question, because we're here in this fractional world, and your Schrödinger equation basically was just not fractional. So if we put fractional derivative on the left-hand side, will your result go through?
Okay, so first of all, the Lévy noise is fractional here. And so I was thinking about the talk, but the question is good. I mean, actually, I gave earlier talk, which you maybe remember, where I was talking about what can be done in the Gaussian case described for the fractional powers. So there are two open questions about this talk. One is whether this result generalizes to fractional Schrödinger equation. I don't know. That is a very first open question. It could be very simple, because maybe one only needs to verify what is the important part is verify whether the Strichartz estimates are true. And this maybe is that checking the literature that such Strichartz estimates of fractional fractional Schrödinger equations are true. The second part is actually more difficult, which would be because we considered here both cases simultaneously, focusing, defocusing, but the sigma was small that it is. So now, if I allow the case of defocusing nonlinearities, in most cases, one has also global solution. So we don't even know whether it is case with Laplacian, or we don't even know where we neither know whether it is true for fractional Laplacian. So this is a very open question. Now, since you mentioned you can write, if you take this fractional this problem, you can write it down in form of generator, where you will have some fractional operator in the generator. Yes, could you solve this problem the way you would like to solve? I mean, without probability, but solving the Martinger problem directly for generator. That is, I don't know neither.
Any more questions? Yeah.
This is, first of all, a remark concerning Vasily's question. The problem here with the fractional time is that the nonlinear part of the operator is not Lipschitz. So you cannot use the usual rewriting it as an integral equation with this t, with the kernel coming from the fractional time inside the integral and so on, and then just use basically Grunwald-Bellman technique to show that it's a fixed point and then solve it this way. That's impossible. However, the nonlinear part is monotone, yeah, by its very definition, so as a convex functional. And then I think one can do something like a Peano approach to find a solution by compactness argument. So it is not hopeless to do also fractional time in this situation. You won't get uniqueness right away, but I think you get uniqueness at the end, again, using the monotonicity of this, because you have a special polynomial of u to the power u to the p minus 1. So I think that is hope to do this. But the sorry, yeah, I have a second question. The second question is what we did with Deng And also with Viore Barbu, we also studied asymptotics of the solution to the stochastic Schrödinger equation. So we proved scattering, for instance, or we proved that non-explosion with high probability in the supercritical case and so on. Do you think you can do the same for the Lévy case? Because it seems to me that the techniques should be not so much different from when you have the usual Gaussian noise.
So let me answer your question. So first of all, your first comment, I think Vasily had something different in mind that you had in mind, because at least I have understood Vasily what he was asking about fractional Laplacian.
Well, I asked actually both fractional Laplacian.
So in the way I answered Vasily from the point of view of fractional Laplacian, not fractional time derivative. So I don't know a fractional time derivative. I mean, I have asked questions some participant here whether, for instance, if you define equation not even much simpler with fractional derivative, can you actually prove something like mass invariance? So we have some discussion about fractional equation with fractional in time. I don't know the answer. But what was your second question? The scattering. Okay, so I don't know. So for instance, if I don't know your paper about scattering, I know your earlier paper. So if my understanding, you use the Dawes-Sussman transformation. And so if I consider bilinear equation here, I think you can do a lot of similar results. You change your transformation to suit the Lévy processes. How difficult it will be, I don't know. So for instance, concerning this question of, so I don't know at all. We have a paper with Lutz Weiss and Fabian about uniqueness in critical case for Gaussian noise, which is actually also in our paper bilinear noise. But we don't use the transformation. I asked somebody to look at this question, whether you can prove uniqueness in this critical case also using the Dawes-Sussman transformation, and no result. So I think a lot of things can go through as always goes through. Yeah, so I would be not surprised that also your result about scattering would be possible to generalize to this situation. So they're open questions, yes. Yeah, I know that. I know the existence of the paper. I don't know what is exactly in the paper. So I think probably yes, but maybe with some work.
So online, there are no questions. You can still open your mic and ask a question. But if there are no more questions, then I'd say we close the session and we thank the speaker and all speakers of the morning.